Greetings, this is Professor Roman. Let us continue the field theory lectures. Last time we talked about field extensions, basically subfields of a field. The set sub E of all subfields of a field E forms an intersection structure. I mentioned this last time, and we've discussed it in detail in the other courses. An intersection structure is simply a family of subsets of a parent set that is closed under intersection. So in this case, the intersection of any family of subfields of a field E is again a subfield. And intersection structures are complete lattices where the meet of a family of subfields is its intersection, and the join is rather more complicated. It's almost never the union, but it is the smallest subfield that contains all of the subfields in the family. This looks like a typo here. That should be E. Incidentally, I should mention this. By the time I release all of these lectures in this course, along with the book, these corrections that I am making will be incorporated into the book. Okay. So in a sense, you're seeing the proofreading of the book as it happens, but by the time the book is available, all the proofreading will be finished. In field theory, the join of a family of subfields is referred to as the composite or compositum of the subfields. The term join is seldom used. And also, as is customary, if we have a finite number of subfields of a field, I think I'll change this to E as well, then we'll denote the join, which could be denoted this way, simply as a product. So this signifies the smallest subfield containing each of these subfields. Now it's important to note that the composite of fields is defined only when the fields are subfields of a single parent field. And so whenever we form a composite, it will be with that understanding. If I say take the composite of the fields F and G, we will tacitly understand that both of those fields belong to a bigger field. So, the family sub F of all subfields of a field F is an intersection structure and therefore a complete lattice where meet is intersection. The largest or top field is F itself, the parent field. A field is a subfield of itself. And the bottom or smallest element is the prime subfield of the parent. The composite can be described more constructively using the following definition. Let FE be a field extension, let S be a subset of E. This is a more general definition that we're going to need right now, but we'll need this more general version a bit later. A monomial in S is just a product of elements from S. So that can be written using exponents, non-negative exponents, or you can just write it out as a product of individual elements with no exponents. But this is going to be convenient for us. So the SI's belong to the set S, and the exponents are non-negative. A polynomial in S over F, that's the smaller field, is a linear combination of monomials with coefficients belonging to F. A rational function in S over F is a quotient of polynomials, where of course the denominator is non-zero. Now we can say that if we have a family of subfields of a field E, the composite consists of all the rational functions whose numerator and denominator are sums of monomials in the union of the family members. And again, the denominator must be non-zero. Another way to say that in symbols is if F is the prime subfield of E, then the join of the family of subfields is the set of all rational functions, so F and G are polynomials, the alpha I, and polynomials over the prime subfield. And alpha I belongs to the union of the family of the fields in the family for all I, and the denominator is non-zero. Now, there's a reason why I use the prime subfield here, and I think it's important for you to think about that and understand why I introduced that here. I didn't mention it in the first description, but I didn't say these were rational functions over anything. I said the numerators and denominators are sums of monomials. So if that's worth giving that some thought. Note that each element of the join of a family of subfields involves only a finite number of elements from the union, and so is therefore contained in the composite or join of a finite number of fields from the family. Of course, this is meaningful when E is an infinite family of subfields. An individual element will belong to a finite join, a join of a finite number of members of the family. Okay. So if we have a field extension, Fe, and if K and L are intermediate fields, that means they contain F and are contained in E, then their composite, as we've just defined, is the smallest subfield of E that contains both K and L. We can do something a little more general as follows. If Fe is a field extension, and S is any non-empty subset of E, then the smallest subfield of E that contains both F and the set S is denoted this way, F of S. And if S is a finite family, then we would write it this way. Don't confuse this with at this moment with the set of polynomials in the alphas over F. This has a different meaning, which we'll get to, different terminology, which we'll get to in a minute. And this set S is said to generate this field, F of S over F. So when you look at this expression, you should think this is the first of all, F, the field F, and the set S belong to a parent field, E, and that this is the smallest subfield of E that contains both F and S. if S was a field, we could just write Fs or F join S. But this is the notation we're using when S is a set. To see that this field must exist, since the parent field E contains both F and S, the family, which I wrote script F, of all subfields of the parent that contain both the field F and the set S is non-empty, contains the parent E, and so its intersection, the intersection of this family, will be the smallest subfield of E that contains both F and S. So F of S is the intersection of all intermediate fields between F and E that contain S. Therefore, it contains F and S. This field is sometimes referred to as the adjoining of S to F. Okay. The composite KL of two fields, subfields of E, this is a special case of the adjoining, because the composite KL is the same as, it's the smallest subfield of E containing both K and L, so it could be written this way. Here L would be thought of just as a set using this notation. It's also equal to this, and it's equal to the adjoining 2F of the union of K and L. You may want to give this some thought. It's quite possibly new to you, this idea of adjoining of composite and of adjoining of a set to a subfield. So it's worth dwelling on it until it seems pretty clear. And again, I say here just because it's important to emphasize, this field, this adjoining, makes sense only when both F, the field F and the set S are contained in a larger field. So we will always assume that's the case, even if we don't explicitly mention that parent field. Using the previous definition of monomial, polynomial, and rational function, we can describe the adjoining of S to F as the set of all rational functions in elements of the set S. We're going to do a lot of adjoining, so it's important to be comfortable with this idea. Okay. We've done similar things in the other courses. The smallest subspace containing a certain subset, and so on. Okay. Adjoining of a set to a field doesn't have to be done all at once in the following sense. If we have a field extension Fe and we have two sets, S and T, subsets of E, then if we first adjoin S to F, that'll give us another subfield of E. We can then adjoin T. That's the same as adjoining the union, S union T, to F. And so in particular, when the sets are finite, and this is going to be quite common for us, the adjoining of alpha 1 through alpha n to F can be done in two stages. We can adjoin some of the alphas first and then adjoin the other alphas. This result should seem, well, I hate to say it, but almost obvious. But just because it may seem that way doesn't mean some effort shouldn't be made to write down a proof that will convince even the most die-hard naysayers. So here is such a proof, and I'm not going to go over it because I would urge you to construct the proof yourself, and then you can compare it with what I wrote. Okay. As we're going to see, it's going to be often very convenient to decompose a field extension of this form into a tower of length n by adjoining one element at a time. And that can also be written this way, just different notation. And this is going to be very handy for us. Okay, let's talk about algebraic elements. If FE is an extension, then the elements of E can be classified into two types based on their algebraic nature with respect to the base field. An element alpha in E is algebraic over the base field F if alpha is a root of some non-zero polynomial over F. The roots of polynomials are the algebraic elements. If alpha is not algebraic, it's said to be transcendental over F. It's also said to be algebraically independent over F, or to be an independent variable over F, or to have no algebraic dependencies over F. We're going to talk in a later chapter about algebraic independence in some detail. But for now, you can take that to mean transcendental. Now, you're also familiar with the idea of a set of independent variables, like polynomials in two variables, for example, or three variables, or whatever. A non-empty set S of E is a set of independent variables over F if each element of the set is an independent variable over the field you get by adjoining the rest of the elements of S to the base field F. Okay. There's something here to be very cautious of. The independence of a set of variables is, if you look at this definition, it depends on the entire set. You could have two variables, each of which is independent over F, but that doesn't mean the set of those two variables is a set of independent variables. Okay. I'm going to say that again. You could have two variables, you could have two elements of E, each of which is independent over F, each of which is an independent variable over F. But the set consisting of those two elements need not be a set of independent variables. Okay? And there's a very simple example, so I'm going to let you think on that, because this is a critical point. Here's an example for this extension, the reals extension of the rationals. Square root of 2 is algebraic over Q because it's the root of a polynomial over Q. On the other hand, the real numbers pi and e are not algebraic over Q. They're transcendental over Q because they are not the roots of any rational polynomial. Now, the proof of the transcendence of pi and e is actually quite complicated. Well, pi and e are somewhat complicated. And it's not something I can really go into in this book. It would take us too far away from our main goals. So I'll have to leave that for another time, another course, or whatnot. You can certainly look it up on the internet. And I can't resist mentioning something which may not mean anything to you if you've never watched Star Trek, the TV series, the original series. But there is a valid point here. Don't confuse the notions of irrational and transcendental for real numbers. They're not the same thing. There was an episode of Star Trek I remember, and it caught my attention for obvious reasons, when Spock says, quote, the value of, he's trying to tie up the ship's computer. So he says, the value of pi is a transcendental figure without resolution. And so he's making the computer compute the value of pi, and of course it can never do that precisely, and so it ties up the computer. Well, pi is without resolution because it's irrational, not because it's transcendental. Unless, of course, something we don't know behind the scenes, and that Spock had said to the computer, find me a non-zero rational polynomial satisfied by pi. That it can't do. But presumably the computer then would have said, well, you can't do that. So he must have said compute pi precisely, compute the exact value of pi, which it can't do. So that's this Star Trek lesson for today. In general, the question of whether an element is algebraic or transcendental over a base field is quite hard. As a matter of fact, there are many real numbers whose status over the rational field is as yet unknown. We don't know whether they're algebraic or transcendental. And one such number is the so-called Catalan constant, which is defined this way. And what's interesting about this number is we don't even know if it's rational or irrational, let alone transcendental. Okay, so the subject of transcendence is quite complex. We're mostly, in this course, we will mostly concentrate on algebraic elements and algebraic extensions, which I'll define for you. The Galois theory is set in the context of algebraic extensions. It's only in the one chapter, well, a little bit here, I think, at the end, and in the one chapter, short chapter on algebraic independence, where we'll discuss transcendence in any detail. If an element alpha is algebraic over F, then the set of all polynomials over the base field that are satisfied by alpha, so that's this set, is non-empty and in fact is a non-zero ideal in this principal ideal domain, F square bracket X. And it is therefore generated by a unique monic polynomial. It wouldn't be unique if we didn't require it to be monic. So we'll call that P of X. This is an extremely important polynomial. It's called the minimal polynomial of the element alpha over the base field F. And I'm going to use a variety of notations depending on context. Sometimes this notation here mentions both alpha and F, which is required, and has the variable X. If I don't need the variable, I might use this notation. There's no subscripts, and so it may be more readable. This notation will work only if the field, the base field F, is specified in advance, but it sometimes makes things more readable. So I'll use one of these three notations depending on the context. And so the minimal polynomial generates this ideal. And we can characterize minimal polynomials in three ways. So we have a field extension, element alpha and E, that's algebraic over F. It's kind of too bad, but I've never seen a notation for alpha as algebraic over F, and I didn't feel like trying to invent one. So, and among all polynomials in F square bracket X, the minimal polynomial is the unique monic irreducible polynomial satisfied by alpha, the unique monic polynomial of smallest degree satisfied by alpha. It's also the unique monic polynomial m of x with the property that for all polynomials p of x, p of alpha is 0 if and only if m of x divides p of x. So p of x has to be a multiple of the minimal polynomial in order to be satisfied by alpha. Say it a different way, the set of all polynomials satisfied by alpha is precisely the set of all multiples of the minimal polynomial. That's what this says. Okay. Because of these characterizations, the minimal polynomial of alpha is also known as the irreducible polynomial of alpha. For some reason, I've never much liked that term, so I always use the term minimal polynomial. So there are exactly two possibilities for an arbitrary polynomial. It either is satisfied by alpha or it's not, or put differently, it's either a multiple of the minimal polynomial or it is relatively prime to the minimal polynomial. Because if it's not a multiple, since the minimal polynomial is irreducible, the two have to be relatively prime, no common factors. If Fe is a field extension, then two algebraic elements, alpha and beta and E, are said to be conjugate over the base field F if they have the same minimal polynomial over F. If alpha and beta are conjugate over F, then for any polynomial p of x over F, p of alpha is 0 if and only if p of beta is 0. And so, in other words, conjugate elements satisfy the same polynomials. They have the same minimal polynomial, they satisfy the same polynomials. And I would urge you to produce a one-sentence or two-sentence proof of that. Here's an example. Let alpha be the square root of 1 plus square root of 3. If we square alpha, we get alpha squared equals 1 plus square root of 3. Squaring again, alpha to the fourth is 4 plus 2 square root of 3. So alpha to the fourth minus 2 alpha squared minus 2 is 0. And so alpha is a root of this quartic polynomial. Now we can use Eisenstein's criterion with the prime equal to 2 to show that this is irreducible. It's monic, it's irreducible, it's satisfied by alpha, and therefore it is the minimal polynomial of alpha over Q.